A while ago, I did a series of videos on this DC shuttle circuit, and since then a number of people have asked me how I went about reverse engineering it and whether I could give a bit more detail on the process that I followed. I'm hoping this video will give that detail. If you're looking for trains running, I'm afraid this is not going to be the right video to watch. This will be mainly electronic circuit stuff. So, a bit of background. A friend of mine had bought a number of these devices, and two had gone faulty. Now, the manufacturer was no longer manufacturing these, no longer supporting them. So I volunteered to help to see if I could repair the two dead ones and perhaps end up supporting the remaining ones in the future. So let's address the elephant in the room to start with, and that is the copyright Andy Kiro on this board. Now, copyright, you can copyright the software on the board if there is any. You can copyright the silk screen diagram, the silk screen layout, and you can copyright any circuit diagrams that pertain to a particular circuit. You cannot copyright the circuit itself, and it's the circuit that I'm trying to reverse engineer. There is no way for me to reverse engineer the software if there is software on board. I just want to get the boards working. So let me take you through the steps that I went through to try and fix this device. And again, let me reiterate that if Andy were still around and supporting this product, then I would just simply have contacted him rather than trying to reverse engineer the product. Right. So that aside, let's have a look at it and see what we've got. Well, the obvious components are the big capacitors. There's a couple of LEDs. There are resistors and a potentiometer. There's what is probably what actually is a full bridge rectifier. There are these two ICs, which are the big unknowns. There's a device up here which looks like a voltage regulator. These three resistors down here, these are 10k resistors, and that's a 10k resistor. That's a 1k, and that's a 1k. Brown, black, red is 1000 ohm resistor. Brown, black, orange is a 10,000 ohm resistor. And this one in the middle is doing my head in because it's triggering my OCD, because although it really doesn't matter which way around in a circuit you orient a resistor, you could just have put that the other way around to be in line with these other two. Anyway, let's move on. Right, and on the other side of the board, this is a single-sided PCB, or printed circuit board. So what I tend to do, because this is the other side, what I tend to do is to flip this image horizontally, that is left to right, so that when we look at the other side of the board, you can match up that large IC, for example, with its footprint here, and the voltage regulator comes down here in the bottom right hand corner. Just makes life a little easier when we're trying to trace the circuit through. Now, I have never seen an IC like this before, where the pins are connected sort of east to west like that, except for the bottom two. And obviously this, if I look at this this thing here, if I go back a step, that is the output to the track. So we have power coming in this side of the track, a bit of processing here, and power going out there. So this IC looks to be a driver of some sort, and you can tell that by the thick tracks, because they're going to be passing more current, and it's also connected directly to the output. So that is a driver. I originally thought it was sort of a quad pack of transistors just to drive the output, but I'm getting ahead of myself here. What I want to do, I want to identify these ICs, and so a straightforward way of doing that is to see where the power is connected. So let's have a look at, let's start at this full bridge rectifier down here. These are the pins that are on the power input connector, and they go directly to these two diagonal pins on the full bridge rectifier. Now, full bridge rectifier outputs a positive and a negative voltage here, depending on the input voltage. I'm going to call them plus 12 volts and 0 volts, just for convenience. And what I did next was to take that diagram and trace through both the 12 volts, which I've shown in pink, and the 0 volts, which I've shown in black. Now you can see the 12 volts only goes to 2 locations, and the 0 volts goes, as you might expect, all over the PCB. There's a gap in the 12 volts here, because if I go back to here, this is a 0 ohm resistor. It's quite commonly used in single-sided circuit boards, because you often get a case where you want to connect this pin here to this pin here, but you've got 2 tracks in the way. Because it's only a single-sided board, the only way to get there is to take a link on the other side of the board. Right, so that shows an interesting arrangement here in that driver circuit. It also sort of confirms that this is a voltage regulator. So what's happening is it's taking the 12 volts and ground and producing a lower voltage from it. So let's assume that's 5 volts for now, and let's trace that through. Now there we have the 5 volts again going most places on the board, and it goes to the top 2 pins of that IC and the very bottom right pin there. If we look at the 8-pin device, we can see that it's taking 5 volts on the top left hand corner and 0 volts on its top right. Now I have done some work with PIC microprocessors in the past, and by coincidence I was looking at a PIC 12F 675 about a year before I came across this circuit, so I'm fairly sure that was a well, I became fairly sure that was a PIC 12F 675. So having established that, I checked the data sheet for the 675, and the inputs match. The 5 volt and 0 volt inputs match. So then the interesting part would be to look at the output pins from the 675 and see which ones go to this driver device. So I traced those here in blue, and this is pin 3, goes to those 2 pins. Pin 5 goes to those 2 pins. Now as well as that, there is a pull down resistor. That's one of the 10k resistors, and that is one of the 10k resistors. So that then gives me all the information I need to try to identify this IC, because we've got where it takes its 0 volts, we've got the 5 volt connections, we've got a 12 volt connection, and we've got the inputs from the microprocessor, which would then be an enable of some form. So the next step then is to dig through data sheets and see if we can find an IC which matches that pinout. And I have to admit to having wasted a lot of time searching for quad transistor packages until I realized what we're actually doing here is driving a motor. So what I should have been looking for was a motor driver package, and that led me to this device, which is the L293D. And looking at the voltage input pins, the enable inputs, the 4 grounds. Now that's quite characteristic, because this is a motor driver. It can generate quite a lot of heat, or dissipate quite a lot of heat, and it'll need typically 4 ground pins on a big ground plane to help dissipate the heat. The inputs and outputs are, remember, they are connected together across the chip. And I found an application note which confirms that you can safely parallel up output 1 and output 4 an output 2 and output 3, just to give a bit more current driving capability. So the next step was for me to put this together as a circuit diagram. And here we have the circuit diagram. I put this together with Easy EDA from JLC PCB because I wanted to get some of the PCBs manufactured anyway. And for some reason I designed this circuit logically running from right to left instead of what you would normally do, left to right. But there we are. On the right hand side here we have the power input from a DC model trend controller, although that could just be a 12 volt power supply. It runs through this full bridge rectifier, which produces a ground output and a 12 volt output. 12 volt output goes into this voltage regulator, which generates 5 volts, which is used by the rest of the system. Everything else runs on about 5 volts. The PIC microcontroller controls the timing of the outputs of the motor driver. The timing is derived from this trimmer pot setting. Let me see, what else do we have? This is the motor driver, which drives the outputs directly. There's a bipolar capacitor across the output, just to smooth the output, and it's bipolar so that you can have drive the locomotive in either direction without damaging that capacitor. Normally capacitors don't like being driven the wrong way around. There's a bi-color LED here which sits across the two outputs, and in one direction it'll light up yellow and the other direction it'll light up red. There's a standard red LED which is driven from the 5 volt line, simply as an indication that the 5 volt line's working. And that's it. Apart from the software in the PIC, which we'll do later in the video. As I say, I wanted to make some of these boards myself, so I'll in the next step I'll show you how I laid out the PCB. Back in a second. Right, so now I've got the circuit diagram for the module, and that gives me enough information to fault find and hopefully repair any failed modules. So the next step I thought would be a bit of fun, would be to take the circuit and design my own board based upon a similar circuit. And here we are. I'm using Easy EDA from JLC PCB. It's a company that I've used before to manufacture PCBs, or printed circuit boards. And this looks a bit of a mess to start with, but let's say the red, I'm designing a dual layer PCB here, or printed circuit board. The red tracks are on one side of the board and the blue tracks are on another. So for example, let's have a look at the input The two input power lines go directly to that bridge rectifier, and from it we get the ground connection and the 12 volt connection, and we can follow the 12 volt connection up to the voltage regulator, where it also meets the ground, and it produces the 5 volt line. Let me see, on the output side there we have the one output being driven by the driver device, and there's the other output. In hindsight, I think what I would have done, the red tracks are on top of the PCB and the blue ones are below it. So the red tracks are on the component side. I think in hindsight I would have put the red tracks here underneath this this driver device. I would have put them on the other side of the PCB, so that if they get warm, they're on the other side of the PCB. They don't heat the chip so much. That's not really going to be a problem with this circuit. Right, okay, so now I've got the circuit diagram. I can lay out the my device here, my module here. I need to write some software to go into the PIC. So let me take you through that in the next section. And here we have the software, and we can begin with an embarrassing schoolboy error. This header comment block was the original from software that I was writing during lockdown for an inertial train controller, a DC controller with inertia and momentum controls. Never quite got that finished. Obviously I've reused this file for the shuttle controller, but I didn't update the header block. Oh dear. Right, so what do we have? This is standard setting up the PIC hardware. I'm sorry, this is written in the JAL language, or just another language. Right, so the next bit of code I've written is a half-second delay. The delay in JAL is best around microseconds. So to have any large large delays, you have to have a very large number in there. So I just had a little function I could call that gives me a half-second delay, and I can call it with a smaller number. Doesn't make a lot of difference at all. So here we go. Enable the hardware, enable the digital I/O, set up some meaningful names for the various I/O pins, declare their direction in the hardware, so that the hardware is set up to configure them as either an output or an input. Set all the outputs off. Enable the analog to digital hardware so that it can read the value from the trimmer potentiometer, and to just do a little delay on start, and then we go into our main loop. So we have a forever loop reading the potentiometer. Now this is where my software varies from Andy's original software, in that his only ever read the potentiometer on power up. Mine reads it every time we go around this loop, so that in Andy's software, to change the delay, you had to switch the thing off and on again, which I find quite frustrating when you're setting it up to begin with. Obviously, once it's set up, you just leave it; it doesn't make any difference. But what I'm doing now is I'm allowing the software to be changed every cycle around this loop. So here we go with the control of the motors. So let's go. We run forwards for the delay amount, which was defined up here, and which came from the potentiometer. So we run forwards for that delay. We stop for a short delay. Now I've got a 5-second delay fixed, and then we run reverse, and then we just cycle round. And that's it. That's all there is to it. I'll attach this software to the comments of the file, or the comments of the video. Right. Okay. So the next step then would be to buy the components, put the get the PCBs manufactured, and solder the whole thing together. I think I'll do that as a separate video, because this one's getting a bit long. So, okay, thank you very much for watching this, and hopefully I'll be back in a while with a kit build. Right, all the best. Thank you. Bye.